Thank you, Noah, and thank you for having me here today. So yeah, my name is Sebastian. I'm working at lithoz. So I started as a CAD/CAM engineer by training, and I did my apprenticeship at W&H Dentalwerk. Most of dentists know them, or as well for laboratory equipment. So I worked there for 5 years as a CAD/CAM engineer, and after that, went to Vienna and did my first experience in 3D printing, worked for a startup as application engineer, learned a lot of different printing technologies and materials, mainly focus on polymers. And since more than a year right now, I'm working for lithoz as an expert and working mostly giving lectures and giving lectures for new customers, for example, and involved in a lot of projects regarding dental, for example, cranium, facial area, and microsurgery.
Yeah, and I know Lithos has been in the aerospace and medical field for a long time, and it's a really well-known brand and company there. But to the dental space, it's a bit new. So why don't you tell the audience tuning in, what is Lithos? What do you guys focus on? What do you guys do?
So on that point, I'm going to share my presentation to give you a few pictures for lithoz. Yeah. And 1 second. So I'm going to share it in here.
And before we forget, the topic for today's webinar to everyone tuning in is how to elevate your lab with next-gen tech featuring 3D printed lithium disilicate. Hopefully you know what we're talking about if you're tuning in and watching the webinar, but I'll let you take it away, Sebastian.
Perfect. So you see my screen right now?
Yep.
Perfect. Okay, so yeah, welcome to lithoz. I've prepared a slide over here. And this slide is basically just an overview as we talked about space and aerospace. lithoz already had some projects where you already know us from the media maybe. So as we already printed some parts for a biofabrication facility on the ISS, we also had a project with the European Space Agency of printing moon dust, for example. And also we printed the arc reactor of Iron Man. So this main component of its suit, but this was a from Mythbusters, maybe you saw that video, but we mainly focusing on high performance ceramics. So here you have an overview of all different various materials we are able to print. And for us is interesting the medical applications here in our field. So sorry, actually, I don't know why it's not worked. Okay, so now you see my slide.
Yeah.
You see the overview of the different materials we're capable of print. And I think most interesting is here the medical applications in here, where you see from a dental side, for sure, zirconia is interesting, but also hydroxyapatite and tricalcium phosphate. And what we are focusing today is the lithium disilicate. Here, an overview about our company. So lithoz was founded in 2011 as a spin-off of the Technical University in Vienna. And we offer a full solution of 3D printers, materials, and the software. In Vienna, we develop and produce all those components. So we have around 150 employees in total on 4 different locations. So 2 of them in Austria and 1 in the US, so in state New York, in Troy, and 1 in China. So we have the quality management system ISO 9001 already, and by next year we'll have the 13485 done. But this is very important for our first medical product, which will be the lithium disilicate, the 3D print. And we already sold around 150 machines worldwide, where around 25% of our customers working with 2 or more machines. Yeah.
Sorry to cut you off, but do you have a 3D printing center as well, or is that mostly for more niche custom solutions?
Our goal is really focus on the development of the printers and the materials. And we do not have a 3D printing lab, so this is basically up to our customers. We have a few customers, they provide 3D printing service, but our goal is to develop and improve our materials and the hardware, our printers and software.
All right. Well, why don't we dive into how lithium disilcate is 3D printed lithium disilcate is disrupting the dental industry.
So I'm going to show you something about some impressions in here of our production facility, just as you've seen it. So we work in a clean room environment to produce all the materials, and here as well of our printer production, how this looks like basically. And as you said, so why should we print dental restorations? And here I created a slide with a few claims, and what we see with lithium disilicate, we surely have the highest aesthetics. So the material with the highest aesthetics is lithium disilicate, with therefore a very excellent mechanical strength and very easy to characterize. We see that with lithium disilicate we get the most natural restorations done, and for sure the biocompatibility.
I was going to ask, so I know that a lot of people tuning in from the audience are already thinking, how does this, aside from the obvious, being 3D printed, how does this differ from traditional ways of offering lithium disilicate in dentistry?
So the main difference is basically the way how you produce it. So our material in the beginning is different, and the way how you process it is different. But in the end, after you went through our manufacturing process, which I will show you later, you will have the same lithium disilicate as you already know. So you can use the same tools for polishing. You can use the same colors for characterize your restoration. So after the process, you will have basically the same material, the lithium disilicate. Which I have here small notes. So this is jointly developed with Ivoclar, and together we developed that product where Ivoclar provides the powder and lithoz basically creates the printable material and the hardware.
So it's two trusted brands coming together to make an amazing product.
So it's together with Ivoclar we developed that product, but in the end it's a product sold by lithoz.
Gotcha.
So over here I have a picture where I show some 3D printed crowns and maybe also some claims of our technology. What we see is big advantages in here is we have no milling tools. You don't have a diameter compensation, which leads you to very high detailed occlusal surfaces and very natural surfaces. And I think one of our biggest advantages we can see here in the next slide is you can print as well ultra thin veneers with our technology. As I mentioned, we do not use any tools in our manufacturing process. So we do not have any mechanical stress. So we can go down to very, very thin ball thicknesses, down to 300 micron. And this leads us to a non-invasive dentistry. And I think this should be the goal when we talk about dentistry for aesthetics, because for dentists, nothing is better to grind or prepare a healthy tooth for a veneer. So, and for sure as well, the productivity with our technology. So here a number is around 7.5 minutes per restoration. So this truly always depends what type of restoration you have on a build platform. And as you see, you can various indications print in one print shop.
Are you changing the slides, Sebastian?
Sorry. Yeah, I'm changing the slides. Actually, I'm not sure
we're still
why.
The ultra thin. There you go.
Yeah. Okay. Thank you very much.
No.
Yeah, so on the left side, you see our build platform. And yeah, so here we have around 7.5 minutes per restoration. The duration of a print job is around 3 to 4 hours, always depending on the highest restoration on the build platform. And for sure, the toolless projection and the high material efficiency. So we can use really up to 90% of our material for the restoration. So we do not generate any dust in there.
And I think what I especially like about it is, sorry, this is going down on a tangent, but I like how there's minimal disruption to a lab's existing workflow. You know, if you're familiar with mill work, if you're familiar with 3D printing, it's not like you have a crazy post-print process. It's very within the lines, and
it's within the lines, within the tools they already work. So as I said, the material is the same. So here I have as well a comparison between the two technologies, the LCM, our printing technology, and milling, where we see the utilization of the material is here at around 90%, and in milling we are around 20%. And what is also very interesting is the difference between the parallel production we have in our process. So up to 50 restoration in one print shop is generated parallel, as you have in milling, one at a time when you mill or grind lithium disilcate. So as well, we are dust free and a very easy material change. So we later in the next slides, I'm going to show you the process. You will see how the material is incorporated, and this is basically very easy to change and start a print shop. And for sure, the veneers in the last point. So you can print very different indication with lithium disilicate just on one machine without any problems.
Yeah, for me, it's the material utilization. I mean, especially in a lab environment, it doesn't matter how good at nesting you are with a puck, you're going to end up wasting X amount of material, especially when it comes to milling. One of the main benefits of additive manufacturing is really that you're only creating the restoration. You're not cutting it out of something. So there's inherently less material and less resources wasted.
Yeah, that's totally a very important point. And so we see that the printing technologies is a very good technology to progress on that. So now let me show you how our process actually works, our LCM dental process. So this is just
sorry, Sebastian.
No problem.
I completely forgot about all of the questions we're getting in. So Calvin Song from Creodent, hey Calvin, is asking how many units you get per build plate, and I believe you're saying it's approximately 50.
Yeah, it always depends. As we see, when you use a lab, if you go printing of veneers, they are much smaller, and so you can put like up to 50. Maybe 60 is always depending on that. And if you're going like only for molars, and then we see like 25 to 30. So very different parts. So it is hard to say to have here a specific number.
And then what is the estimated print time and the duration of the post-processing? We'll dive into the entire workflow in the upcoming slides. So we'll save that one for later. And then Calvin was also asking, what is the waste percent versus milling? I believe you had that in the slide. It's about 90%.
Yeah, we had that in the slide. So this is, so utilization, we're around by 90%. So, and we see with milling, it's around 20%. So this was kind of number that we investigated due to different questionnaires. So, and so this is around the number that we can use. So 90% of the only material you lose basically. So after your print shop, there's still sticks some material on the surface, and that you need to clean. And this is basically the material you lose during the print process as well, but the support structure.
That's inherent with any 3D printing process though, right?
Yeah.
And Maddie is asking, can I use your material in my DLP printer? I'll let you answer that one, Sebastian.
So that's not possible. So later I'm gonna explain a little bit of something about the material. But I can tell this right now. It's very a highly viscous mass, and so it's for common 3D DLP or SLA print is not possible to process this material. So we have some technical features in our machine to make this possible, basically. So it's on that side, it's not possible to use a different printer.
And then we also have, we're getting actually a lot of questions about the overall workflow. I think the audience is excited.
Yeah. Okay. So let's dive into the.
Let's dive into it.
The workflow, how it basically works. And so yeah, the process changed for you. Just an overview. As we work with the CAD design, we send it to the 3D printer. Then we have the thermal post-processing, in our case, debinding and sintering. And then we have the post-production, post-processing, for example, remove support, staining, glazing, and so on. So let's get more detailed to the CAD design. So yeah, we start with 3D scan. I think this is very familiar. And with an intraoral scan, the next step is design. So for sure, you can use the common softwares like Exocad or 3Shape to generate your design. And after that, you export your file and create a support structure on your restoration. So this is a little bit different if you compare it to milling. I think you have more like less but thicker connection points. We have more and very thin connection points. So this is for us important for the print process. And so at this,
so the supports are more in line with 3D printing than they are with milling supports. Okay,
that's exactly this is the point. So we develop here to get the perfect size of these pinpoints that you afterwards have. You remove the support, you easily only have to finish it on this surface, and then the restoration is done. And yeah, so here this is a different process, and would say at that time the most critical to align and choose the surface where you want to put on the support.
And then this is kind of getting into the you're talking specifically about how nesting and selecting the way you put the supports is different from what you would normally do for 3D printed.
Yeah, and for 3D printing, it's very similar to 3D printing, but it's different to milling, for example.
Oh, sorry, I misunderstood what you're saying.
Yeah, it's basically not integrated in Exocad at that point. So we use here different software. It's Desk Artist right now that we use to create this support structure, but we're developing here to make this step as easy as possible for the dental technician, because this is a very important step.
So there's a separate CAM software that labs will have to use?
Yeah, at this development stage, yes, it is a different software, and and the next step is basically the nesting. This is again a very easy step. So you did your support structure, and then you only need to put it in our slicing software, basically the software which operates the machine, and put them on the surface. So very easy step, and send it to the printer basically. And after you send it to the printer, so here's a small explanation what basically happens. It's again very same as you have it in a DLP or SLA printing process. So we have our build platform, our file or our model, and then we slice it into images. And each image is used and projected on our vet. And then we use blue light to for polymerization of each layer. And so basically our part is created. So in this step, we create the shape with polymerization. So in this printing step, we do not have a full dense ceramic part. We have a composite part. And this leads me to the next slide, to our slurry. So basically the material we use, we call it a slurry. And it's a mixture of ceramic powder on the one hand, and as well a photocurable binder. And this mixture,
and the ceramic powder is made by Ivoclar.
It's made by Ivoclar, yeah. For the lithium disilicate, for that project, is made by Ivoclar. And as we have a very amount of powder and as less binder as possible, so the mass is highly viscous. Maybe you see it on the left picture where the material gets into the vat. And so a lot of, so it's not possible for common printers to process this material. In the next slide, I'm going to show you a small video how our printer is built up, how it looks like. And you basically see that our vat is round, and we have this white blade. It's called Viper blade. You see in the left picture, and this blade coats a very thin layer of ceramic, and then we dip in with the build platform, and the polymerization of the layer starts to create the final part. But let me show you the video, and then you have, I think, a better overview how this printing process works.
Yeah.
So you see here basically the machine, how our machine looks like, and then you see here the printing area where we have here on the top our build platform. The white one is here the Viper blade, and the round vat is where the material is incorporated. So here is one of our biggest advantages, that we only have around 10 grams of our material that needs to be inside that vat. So when you stop a print shop, so basically you don't lose any material, because you can use basically everything what's in that vat, except of a few grams. Mm-hmm. And this Viper blade coats, as you see here, you see this rotation movement of the vat, and the Viper blade, which coats a very thin layers. You see here our dosing system, which pinpoint precise dosing during the print shop. And this is basically how it looks like when we coat the layer. We dive through our slurry and get on the bottom, basically into the heart of the machine, where we see our projection system, optical system. And here you see basically how it works. We project here one slice, one image of the 3D part on the bottom of the vat. And due to that blue light, a polymerization starts in our material. And you see the screen running? 1 second, sorry. I'm so sorry for that. Mm-hmm.
Oh, no worries.
Interesting.
And do you have, I guess, okay. Mm-hmm. I'll wait till we finish the video and then I'll ask the question.
So here we are. Yeah, we have here okay, I don't know why it doesn't work, but yeah. Okay, and here we see the polymerization of that layer and how we create a 3D printed part afterwards. And that's basically all. This is how our printer works.
Okay, well, thanks for the video. Out of curiosity, do you have multiple, I guess, size machines, or is it just kind of one standard size?
This is a video, as you see on the parts, that is created for the industrial sector, and for the industry we have different sizes of the build platform and of the projection systems, which we see for the medical, especially for the dental field. There is only one machine. This is the S65. Which is interesting for the dental field. So the others is more for the industrial area. Yeah.
Gotcha. So for dental applications, there's only one size printer at the moment.
Yeah. Yeah.
Okay.
Yeah. So this is basically how our printing looks like. So after this printing, we have the cleaning, as I mentioned before, is on the surface. There still sticks some material, and after these cleaning steps, we go to the debinding and sintering. And
I think we're, oh, there we go. The slide just changed.
Perfect. And here we have, this is a little bit different to milling, as we have two steps in here. One is debinding and one sintering. And I like to explain it on the left picture in here. So this is a part basically printed from our CEO, Dr. Johannes Homer. And in the left side, you see the part basically directly after printing and cleaning. And you also see an image of the particles. We have in the particles, the yellow, the ceramic particles, and as well some polymer particles. These polymer particles helped us basically to shape the part. And now in the debinding process, we want to get rid of them. Basically, we burn them out. So we use heat to burn out all the polymer, and then we get to the part in the middle where you see only the ceramic particles without any polymer. But we have a very, very low density in here, and so we have the last step, the sintering. And in this step, the sintering and crystallization in the lithium disilicate takes place, and we create the dense and strong part in here.
Very cool. So instead of, in a normal 3D printing process where you would do typical alcohol wash. You're just doing the debinding, which is essentially just using heat.
Yeah, we
and
have
then you
for
go to
sure.
sinter.
Yeah, that's true. So we have for sure, we have a cleaning step in between where we have our own developed solvents to make this cleaning as easy as possible. And then this debinding basically helps us to, get rid of all the polymer inside the part. So we burn out, and after the sintering process, we have basically the full ceramic. So here we are having no composite anymore. So this is the lithium disilicate after this step, as you know, basically from pressing or milling.
And in terms of time, I guess, what's the total time for the post-print process? So after fabrication.
As we're still in the development process of this product, this time amount of the debinding process is one of the most critical steps in here. So but what we know as a time is here that the printing process is around 3 to 4 hours, and the sintering process is as much as you know from lithium disilicate, from pressing, for example. The debinding step is something that we at this time don't have an exact amount of time right now.
Yeah, so, you're still gathering data on it.
Yeah, we're still gathering data on that. Yeah.
Cool. And then, oh, sorry, go ahead.
Have you any question regarding the debinding sintering?
Yeah, if anyone, I have a question from Calvin over at Creo. He's asking, what is the thermal shrinkage from the sintering?
The sintering, so in the full process, we are around 30%. So again, so this is not a number that's very specific right now. So we are around 30%. As in the development process, we in the end try to get as much ceramic in our slurry as possible to get the shrinkage as minimum as possible. But so we see at the moment it's around 30%.
Okay. And he's asking, is that factored in the CAD software?
Yes, so this is in our slicing software. So basically that comes with the machine where we do the nesting in the end. Here we have basically the shrinkage for the part prepared. So here we only select the material, in that case, lithium disilicate, and then the factor is basically the part is prepared in that factor.
Okay. And then we have a couple questions about the material specifically. So why don't we finish going through the workflow, and then we can talk a little bit more about the material.
Yeah, so it's 2 more steps. So I just want to show the removal of the support structure. Here, the laboratory tools, not any specific, something as you know, so the ceramic after our sinter process is the same. So you can work with the material as you know, you have really the same feeling on it, and as well as the staining and glazing. In here, so you can use the same colors as you used before to create basically the natural and final result.
Gotcha.
Yeah, so that's so far on the process.
Now, in terms of, we're actually getting a bunch of questions come in. Moj is asking, what is the shade and variety of the material available? Will the materials be coming in different shades, or is it one standard? And then
when we our goal is to get the materials as soon as possible to the market, and so we see that we're going to start with medium translucency and the most common shades. So this will be A1, A2, and B1.
Okay. And then Arnold is asking, do we have a video that shows the entire process starting from preparation for the 3D printing? You know, if there's any calibration for the 3D printer.
Preparing something, so we have a video, so it's in the finalized step right now. You can always reach out to me. You have my email, so as soon as I have the video, we will give it on YouTube, and I'll send you the link to the video where we dive you to the full process. Starting from preparation, exocut, sending to the machine to see basically the dental workflow video, it's called, and for sure we're gonna send out this. So I think it takes some time, I think a few weeks till we have it done. And at this point we have 2 parts. The video has 2 parts. In the first part we explain the integration basically of exocut, how you can prepare your restoration. The second part is focus on the printing and one part of the sintering. And I think later this year we're going to prepare a video where we talk about the sintering and the post-processing of the part.
Gotcha. And just so everyone has your email, I'd like the marketing team to drop Sebastian's email in the general chat. If you do have any questions that aren't covered in this webinar, please feel free to email Sebastian. We'll also have a poll at the end for those of you who are interested in learning more about the technology, and we'll share your email directly with Sebastian. So stay tuned. We're still getting a bunch of questions coming in about the material and workflow. Maddie is asking, or Patrick is asking, what is the MPa strength versus traditionally processed lithium disilcate?
Again,
Maddie is asking, what is the MPa strength versus traditionally processed lithium disilcate?
Regarding the strength of the material?
Yeah, the strength of the material.
Yeah, so here, so for sure, we still, the FDA approval is still pending, and so we couldn't get any values, give you any values on that. But here as well, our goal is to get the same strengths as you know from IPS Emax Press.
Okay, and yes, that ties perfectly in line with the next question, which Maddie is asking. We know milling lithium disilicate is substantially weaker than pressed lithium disilicate. So what's the strength of this material compared to pressed? And I think you kind of answered that already.
Yeah, so this is the goal that we get here, the same strengths as IPS Emax Press.
Gotcha. And Edwin is asking, do you sinter on the Ivoclar S1, or do you need to use a lithoz machine to sinter and for the post-print process?
The post-processing, so as I mentioned, we have two steps, the debinding and the sintering, and crystallization. And in the debinding, we have two furnaces in here. So we have one debinding furnace. These are not from lithoz. So these are basically, the debinding furnace is provided by Nabertherm. So it's a company in the industry and the ceramic industry, very common. It's a German company. And the sintering and crystallization process, there you can use a program from Ivoclar, for example. Yeah. Okay,
cool. Another attendee is asking, do we need debinding sintering under vacuum furnace? Or debinding under vacuum and max temp is 920.
The debinding is in a much lower temperature and don't need any vacuum. So you only need the vacuum in the sintering crystallization process. So for example, in Programmat from Ivoclar,
And Calvin is asking, what is the sintering time?
Sintering time, I need to look up on that. I think for sure numbers is very difficult on that to say. It's, I think, in a range of 1 to 3 hours for sure. So this is as well something we need to evaluate and find out the perfect time to get to don't get any bending in the material, basically. So this is one of the most critical things in here. And as I mentioned before, that we print with support structures, and these very fine connection points helps us a lot to avoid here the bending and have a very precise part in the end.
Okay, and Moj is asking, are there specific stains and glazes that you need to use, or is it open to user preference?
You can use a preference. So if you work with lithium disilicate, especially with Ivoclar, you can use the same stains and glaze you already used. So because after our debinding and sintering process, we have a lithium disilicate, as you know it from Ivoclar, and it's the same process in staining and glazing.
Okay, and I know we still have lots in the presentation, so I'll let you continue going, Sebastian, but I do encourage the audience, as you have questions, just continue to drop them. And we'll try to address them all by the end.
For sure. So for sure. I think we have some time in the end to answer all the questions. what I've prepared for the next slide is here some dental results in here. So these are basically some veneers by dental technician Josef Schweiger from the LMU in Munich. So he's I would say a friend of lithoz. We work very close with him in this development process. He's a very, very extremely good dental technician and helps us a lot to get to know more in the world of dental technicians. And so he printed some very fine veneers in here where we can see we partly can go a bit thinner than those 300 microns. And so it's his article that he wrote about the process, how it works, how the processing works from his perspective. And so here's the try-in with, we call it the ultra thin veneers he printed. So if you're interested on the article, just reach out to me, send you that one. And for sure, have a quote in here that he's also really likes to work with our technology. So as he sees with the 3D printing of lithium disilicate, we really this very high attention to detail, precise fit, and straightforward workflow. And another result I want to show you here is done by the dental technician Alvaro Roberto, and he showed us with one of our restorations. We sent him a cutback technique, so he prepared it basically for a cutback and showed us here this I would say very beautiful result in here. And another result in here is as well the diastema closure. Here we have a paper made together with the Charité in Berlin. So for sure, please reach out to me if you need any more information on that. So where we just want to showcase this diastema closure, where it's very important to get very thin edges. And this looked very, very well on that. And as well, a very impressive try-in here is as well in the same paper with the Charité in Berlin. And here we have the incisors and the canines were printed with our technology, were processed and characterized. And then here, took a picture in that try-in. And this was done by Dr. Alexey Unkovsky. And as well a quote from him, and she's as well impressed about the aesthetics of our technology and the fit. And so in the next slide, so what's in for you, I have prepared a small, I would say a business case in 3 slides to visualize basically the advantages of our technology. When you see here compared to milling, when we take a block of lithium disilicate with amount around 7.8 grams, you can go for one indication, one restorations. And the most of it is basically, you can't use. And if you use the same amount of material and go, for example, one of those ultra thin veneers, you can go up to 5 veneers with just that amount of material. And this allows us that we use almost every material that's in the vat. And what you see here again is the shaping time comparison on the left side in minutes, as we have in printing the parallel production with up to 50 restorations. And when you go milling lithium disilicate, you have just one after one. And so this leads us that we can get much, much faster in our printing process. And when we take a look at the costs of the consumables, in our process, the only consumables is basically the cleaning solvent, and on your vat you have a sheet, a transparent sheet, which needs to be changed 1, maximum 2 times if you have like mass production per month. And compared to milling, where you have the very expensive tools, for example, so here we see a lot more costs that you save with 3D printing. And in the next slide, this is as well just an overview about the production costs of one restoration over numbers. And here we see that we are at around 5,000 restorations. Here we have our point where we mark, and we are cheaper than milling. So here we see that's basically also the message that we with this technology reach out to bigger labs who won't go with a lot of amount of restorations.
Mm-hmm. Yeah, so I think something important to note with this graph too is it's a bit that's in line with what you'd see for most major equipment purchases for a large lab, right?
Yeah.
Anything from like even with a traditional 3D printer, especially one that's production oriented, you would see the same type of graph.
And when
go ahead, sorry.
And when we talk about the investment, so it's basically why the graphic is on the left side that high. So we are around $500,000 investment for the whole equipment to start printing. And this is basically why up to the first 1,000 restorations, you're more expensive than milling, but after that you go down and then you reduce costs up to 50% on your daily business. And this, I think, is a very impressive number.
Yeah. Exactly. So the main benefits of adopting this, well, there are a lot, but if you could boil it down, it'd really be saving time, and saving material and saving cost.
That's the main points for sure. And the possibility to use a lot of indications, for example, a big molar and a very fine, thin veneer on the same build platform, in the same print shop, on the same technology.
Interesting. Yeah. And I was going to ask, so we've been talking a lot about, how you're saving time, you're saving cost, it's a lot more efficient, you save more material. But I was wondering, what are some of the limitations of 3D printed lithium disilicate? I mean, the technology sounds cool, it looks amazing, but surely there have to be some current limitations. So is there any drawbacks that you could talk about?
The biggest limitation I would say right now is that it's not available on the market at this point. So that's, I would say, the biggest limitation. And maybe as we see here in the business case, the high volume of production that a dental lab needs to afford our technology. And as well, the initial cost. I would say the biggest drawbacks in that. But if you're a dental lab who produces that amount of restorations and really want to see how easy it is to manufacture lithium disilicate, I think that is the best way to go through printing.
I was also out of curiosity, I was wondering, are there any concerns about the solubility of 3D printed lithium disilicate? I know resin material solubility is pretty critical since you don't want the restoration dissolving in the patient's mouth. Yeah,
so it is also important for us that we are in the end a full dense ceramic. So we are not a composite, we are not 30, we are not 50% ceramic. After printing, we are 100% ceramic. And so here we have basically no struggles with any solubility of the material afterwards.
Okay.